Hello everyone, welcome back to C++ for Java programmers. This is the week 4 lecture. As we get started, if you guys could go to Canvas and download the template and the code for today, you'll have that available while I go through the rest of the announcements. First, I want to just say thank you to everybody for all the messages when I was basically out of commission last week. I really appreciate it. Let me start with Mike's health. That's probably the most interesting one. So a week ago Sunday, I was driving back from a wedding and started experiencing chest pain. As I approached Dubuque, I kept thinking, if this gets worse, I'm going to stop. If it gets worse, I'm going to stop. After I got through Dubuque, I started thinking, I wish I'd stopped. And then when it got worse, I called 911. They helped me get to Platteville, and I spent Sunday night in the hospital in Platteville. I made it all the way to the hospital. And then when I walked into the lobby, as the security nurse was taking my temperature, I collapsed. I woke up in a wheelchair as they were trying to put me into the emergency room hospital bed. My heart had slowed down to about 40 beats per minute, which was not enough to keep me enough blood going to my brain to keep me conscious. So basically, while I was there, they gave me atropine that got my heart going, saved my life. I ruled out heart attack. It was not a heart attack. It was not a blood clot. Those are the two most common reasons that men go to have chest pain and go to the emergency room. The really life-threatening ones anyway. And then COVID. They ruled out COVID. So I don't have any of those. In the morning, I was starting to feel better. They sent me home. They said probably not in any danger of dying, low risk. Met with my primary care physician. I've had a lot of tests done. And so far, they've been able to rule out it's not my heart, which is, I guess, reassuring. They only test for the really big bad things. The fact that they couldn't find what was wrong is a little worrying, but I guess very reassuring at the same time because they've tested for all the things that go horribly wrong. I'm supposed to minimize stress in my life, try and get enough sleep. That's the major reason for this delay is I missed last week and I'm still trying to catch up with everything. So I just want to say thank you. I apologize for how long it's taken for me to get to this lecture. I gotta admit, I prioritized 220 over 368. So you guys got the short end of the stick here. I'm going to try and make sure that it's not an undue burden on you guys as we get caught up. I'm not going to dump a whole lot of work on you all at once. So just rest assured, we'll still get through the entire content for the course, but it'll be spread out. We'll catch up as a little bit each week. All right. So that's kind of where I'm at health-wise. Couple other things. Office hour schedule still the same. I'm back doing regular office hours. Haven't had a lot of visitors because the course was basically on hold, but that should resume. Homework 2, I'm going to write that immediately after I finish this lecture. It's almost finished. I'm almost ready. It's just not perfect yet. I was starting on that before I started having health problems, so it shouldn't be too much longer. And if you do run into any questions or problems, a weird error message that's really common as you're learning C++, go ahead and just post a screenshot of that on Piazza, or if it's got some of your code that I would rather you not share your code, go ahead and just send an email or make your Piazza post private. All right, let's get started. So the plan for the next 2 lectures is to go over the rest of the topics for the first third of the course, the first 5 weeks. And what we're really missing so far is a discussion of primitives and literals. We'll start with primitives today. This is a great place to include enum and the switch statement, which almost always go together. Not necessarily, but frequently. I want to introduce basic functions. C++ allows us to put functions in global scope. With Java, everything is required to be associated with a class. So we'll see how this works here. Very similar to what Java does. And then arrays and pointers will wrap up the first 5 weeks. Now arrays are very closely tied to what we do with primitives, and we'll see they're also very closely tied with pointers. So right after I get done with basic functions, I'm going to go edit the video and see how long it is. It depends on how long I ramble on about some of these things. And then we'll either include arrays we'll start today, or maybe we'll push that to the next lecture. I'm not sure at this point. All right, so let's dive in with some primitives. All right, in Java, we have exactly 8 types of primitives, and that's all you get. These are not considered to be objects, nor are they in C++, so we don't get a lot of the cool object-oriented programming features with these. These are just the basics, close to the hardware, which means that they'll go pretty fast when we do things. All right, couple of things to note. In Java, all of these get a default value. When we flip over to the next slide, we'll see that the default value column is blank. So they're basically all initialized to 0 or null. In C++, that is not going to be true. In fact, I demonstrated last time that when we declare a variable in C++, if we declare an int, for example, it's going to reserve some space in memory for us to store whatever we want, our number. However, it's not going to initialize to 0. We're going to get whatever garbage was in that memory location from the last time we used it. All right, the other thing to note is that the size of all of these primitives in Java, these are actual real numbers, very well defined. An integer is going to be 4 bytes. We're going to get something from about negative 2 billion up to positive 2 billion. Here it is in base 2 representation. Yeah, so let's start taking a look at the primitives in C++. All right, here we go. We have lots of different types. This slide is probably too small for you guys to read. You can download the PDF of the slides and make this bigger. A couple things to note here. We've got lots more types. I didn't even have a default value column. I took that out. There aren't any. We see that this is now up here. This says typical size. There's not an absolute. And in fact, most of these are listed as greater than or equal to something else. They're just guaranteed to be some minimum size, which frequently is based on some other minimum size for a different variable type. A couple of other things I want to just point out while I'm on this slide are we don't have the byte. So up here in Java, we had a single byte primitive. We don't have that in C++. And frequently, if programmers want to use a byte, they'll use a character. So all of the different character types are just numbers on the inside, and we can use them as integers. All right, this table is really too tiny. I went ahead and made some other slides so we can talk about these things in a little more detail. I know it's not the colorful table, but this will get the job done a little better, I think. All right, so I'm going to start out and talk about the integer data types. If we declare an int, and you guys have been doing this for the first 3 weeks of the class it works the same way as in Java. Typically, these are going to be 4 bytes, but we may it's going to be system dependent. We may see that it's either 16, 32, or 64 bytes. I think all the machines I've ever used have used 32-bit integer types. So that gives us about negative 2 billion up to positive 2 billion. C++ also includes a number of modifiers that we can add to describe how many bytes we want to use for our integers. And again, these are not guaranteed. So for example, we can use the modifier short, and that's going to give us at least 2 bytes. And we can also abbreviate this. We don't need to say short int and then, width or whatever we're naming the variable. We can just use the shortcut short. Same deal with long. So in Java, short and long are going to be their own data types. They don't require the word int. They're going to be separate primitives. But in C++, these are considered modifiers. So same deal here with long. This is going to guarantee us at least as big as an int. And typically, on all the machines I've seen, long is exactly the same size as int, at 4 bytes. When we abbreviate this long, it will give us the integer type. There's because these are considered modifiers, there's also a long double. But if you just type long, it's going to give you the integer. It's not going to shortcut to the long double. You need to write out the whole long double to get that. And finally, we have a long integer. And on all the machines I've used, this is going to be 8 bytes typically. But all it is guaranteed to be greater than or equal to the long int. And in fact, all 5 of the, short, int, long, all 4 of these could be exactly the same size, depending on the hardware you're working with. All right, and then the other modifier that we'll find is that we have either signed or unsigned numbers. Oh man, typo, timeout. All right, got the typo fixed. Okay, so we can have either signed or unsigned numbers. This is going to reserve one of the bits, as we represent the number, to indicate that either it's positive or negative. So the default is signed values. So just a regular int will permit negative numbers. But what this is going to mean is that the signed bit will go, If we choose to create an unsigned number, we will get all 32 bits to be reserved for numbers. And so we see the range of numbers. It's the exact same number of digits that we get, the exact same number of numbers we can represent, but they'll go from 0 to 4 billion instead of minus 2 billion to positive 2 billion, something like that. And we can combine these modifiers. In fact, we can have an unsigned long integer. This will give us the maximum possible biggest integer we can actually have in C++. And because all of these things are machine dependent, there are built-in functions in C++ that let us figure out how big each of the numbers are. And I'll go demo that in just a second. All right, actually right now seems like a good time to just jump over and demonstrate how to get the size of all the different data types. So the size of all the data types is the function there is called sizeof. That's right here in all of these lines of code. It's found in the header limits, so you'll need to include that in order to get any of these. It'll tell you an error, and I believe it even suggests where to go look for it. Again, typical C++ code will be using namespace standard. Just think of that as magic. I've got my function prototypes here because my functions are defined after I use them. And then in main, the only thing I'm doing is calling the function type sizes. So let's take a look at that. It's going to print out type sizes and then create a very nice list of all the different sizes. So size of bool, it's just going to call the function sizeof. This takes a type, bool here in this case, and these are all going to be released in bytes. And let me just go ahead and run this because the output's easier to read than the code. So right quick, we'll compile this and then we'll run it. All right, so here we go. We'll see that on this machine, this is the CSL machine. We're looking at Royal 03 right now. And this will probably be different on your home computer, particularly if you're using a Mac or Windows machine. May not be the same. And in fact, when I do this lecture live and students are following along, someone raises their hand and said, I got a different number for whatever. So what we'll find is that, so the size of bool, let's start with that one. That's either going to be 1 bit or 1 byte, depending on the machine. I've never actually seen it be 1 bit, but I know that is permitted as a possibility. So C++ is either going to use, whenever it does math with a byte, and a Boolean, it's going to either assign it the value 0 or 1. And if we do arithmetic, because all of these things are just numbers on the inside, it doesn't worry about it. It'll automatically switch it over and it will convert it to an int, whatever that is, with the value either 1 or 0 anytime we do math. So it's going to switch it to a 4-byte data type that's either assigned the value 0 or 1. And we can do the same thing in reverse. We can use most of these data types as Booleans, where it's going to say if it's 0, that's going to be false. If it's non-zero, then it'll be true. So they're basically interchangeable. On this machine, we'll see that the size of a character is 1 byte. On Java, they're going to be 2. In C++, we're going to see that almost all characters are encoded as ASCII. It's just a chart that says, a particular letter is going to be assigned a value of a number because inside the computer, everything is stored as a number. And they'll be using that ASCII encoding. So like A is the number, like lowercase a is the number 97, for example. On this machine, int is 4 bytes. The only thing guaranteed is that it's bigger than the short, greater than or equal to. We'll see that short is using 2 bytes. The long int, it's 8 bytes on this machine. I believe it's 4 on my home computer. Long is exactly the same as the long int here at 8 bytes. This one's interesting, size t. There were a number of questions on Piazza as you guys started working with strings on the last homework assignment. And that's because the size of function for a string, string.length or string.size, returns a data type of size t. This is actually an alias for an unsigned long. So when I give you that warning saying we're trying to compare an int to basically an unsigned long or size t, it was giving a warning there because there's some challenges. Every time you compare signed numbers to unsigned numbers, I believe it converts the signed numbers into unsigned, which can take like a -3 and turn it into just an extraordinarily large number for the comparison because it turns that sign bit, which is a 1 if it's a negative number, and treats it as a real digit, basically the most significant digit in binary. We'll come back in just a second and talk about floats and doubles, but there's not really much more I'm going to say than floats reserve 4 bytes to represent how many digits. Basically, it gives us like 5 or 6 decimal places, so 3.14159, and we're done. That's all you get. Double gives us approximately, double the number of precision there. We get 8 bytes. So something between 12 and 15 decimal places. All right, I think that's... Go ahead, do some experiments with this. If I missed any of the types, remember there was a giant chart with all kinds of things in it. You can go pull that up and experiment and see the size of anything else. And the one place that this is going to be really important, if you're using the old school style memory management from C, where you're using malloc to just grab a block of data, a block of memory to do whatever you want with. If you want that level of control, it is still available in C++. We teach that stuff in CS 354, Machine Organization and Programming. I'm not going to go into it during this course. If you want to learn more, I'm happy to talk about it, ask questions on Piazza. I just got done teaching that course over the summer. It's still fresh in my brain, but I'm not going to do that low-level programming here. All right, so before I begin talking about the literals as we assign them to integer data types, I just wanted to mention a couple things about type properties. I believe this is also found in limits, so you'll need to include limits before you can use these libraries. In fact, right here, it's I see I've got, put this back so I can highlight it. Standard numeric limits. I don't need the STD because I am using namespace STD. This is how it would work. And I just copied and pasted this code from the internet, so it's already there. All right, so here's the idea. I'm going to be looking at type properties. And as I read this code, I've done one thing to make it easy to switch back and forth between other data types. So it's going to print out minimum value for, and then whatever type is. And I'm using type as the name of a variable, and I'm giving it int. So it's just going to print out int right here. It's just a string. Then it's going to call standard numeric limits. And this is going to take a parameter. And that parameter is going to be a type. So this is how C++ does generics. It lets me switch between one data type and another. It's called templating in C++. But I've just created a new type, or maybe a better word would be an alias for a type, so that I can use int in all 5 of these statements right there. So I'm just reassigning the type int, and I'm calling it t. So here I'm going to be using t as the int, and it'll print out all of the data for int. So let me just show you how this works. So I'm going to go grab my command. This will compile it with G++. From the command window in Vim, I can use the exclamation point to execute shell commands. So the compiler would be a shell command. The percent just means the current file. So let me, later in the course when I have multiple files open, I can switch between windows and still use the same command, and it'll just compile the current file. And then the vertical pipe means execute the next shell command after this one finishes, if it finishes successfully. When this compiles, it'll create the default file name a.out, and then I'm just calling that function. I'm creating an executable file, and this will just call it. So let me go ahead and push enter, show you what happens. So here's the idea. It's going to print out the minimum value for a type integer. So this is like -2 billion. The maximum value for type int is about 2 billion. Is it signed? Yes, it is. How many non-signed bits are available? Does it have an infinity? Oh, yeah. Okay, so this is going to depend on the machine you're working on. In Java, there are 3 sort of numbers. There's a not a number, there's a positive infinity, and a negative infinity. C++, those are not guaranteed to exist. It depends on whether you're on a Windows machine, a Linux machine, a Mac, the platform you're working on. So just you can get that information about the machine you're working with from these type properties. All right, I'm going to push enter to continue. Now here's what I mean. If I go back and use the unsigned version, so I'm just going to add the word unsigned right there in 2 places. So this will change the text that it prints out, and this will change the type that we're sending to numeric limits, and we'll get data about the minimum for the unsigned version. So I'm going to go ahead, write this, then we will just compile and run this again. And now we have the same thing. Timeout, let me see what I did wrong. Okay, got it. It doesn't accept that % shortcut for the current file name if I'm chaining commands together. All right, so let me just run this with the real file name. It's going to create /a.out, and we'll run that. And here we go. So when we switch this to unsigned integer, so this one changed the text. That was my type data. And I can see now that the minimum value for something that can't be negative is 0. And we get approximately 4 billion, so approximately twice as many integers. It's because it's using that sign bit for a 4-byte data type to give us more. It basically becomes the most significant bit or the most significant digit, and we get a bigger range of numbers. Again, it's not signed, so this one's false. The number of bits available to store real data, 32, and again, there's no infinity available for this data type. All right, so I'm going to leave it here. You guys can try any of those other things and just sort of do some exploring on your own. I'm not going to go through very many of these. In a live lecture, I would take suggestions from the audience, but do it on your own. All right, this seemed like a good time to dive into integer literals a little bit. Literals are just numbers, like straight up numbers that we are telling C++ to use. We're hard coding the numbers. So up here I've got, I just wrote some code to sort of demonstrate some things that totally work. We're allowed to enter integer literals as just decimal numbers. Those are the numbers we work with every day, base 10. We're also permitted to enter them as octal numbers. Octal numbers all begin with the number 0, and Vim is highlighting that for me, that this is an octal number, turning that into purple. The only place I have ever run into trouble using octal numbers in the past is September. So if you're going through putting in the months, January, frequently they'll ask for 2 digits, 01, February 02. You get all the way up to September, which is 09, and all of a sudden it treats all these numbers as octal. So 01 is actually 1 in decimal and octal, absolutely no problem. Over here, it's going to convert it to binary and store it as an integer, binary integer. They all work great up until you get to September, which is 09. Octal uses the digits 0 through 8. There is no 9 available in octal, and it will crash your code. And chances are, by the time it's October 1st right now, this will happen 11 months from now. So this is an error that's going to pop up way in the future when someone enters 09 into your date. Heads up, I would recommend avoiding octal numbers for dates, as that can be a problem. And we're also permitted to use hexadecimal numbers. In this course, I'm not going to use anything but decimal. But in when you get to the low-level machine programming, in like machine programming, organization programming, some of the other operating system courses, we'll find that we use hexadecimal for pointer addresses. I take it back. We'll be doing this next week where I talk about pointer addresses. I'll show you how to get them and why we would ever care. All right, and then a couple other things. If you want to declare a particular number to be of type long, you can add the suffix L. Now, C++ will take either uppercase or lowercase, and it doesn't care. It can tell the difference. But check this out. If I use the lowercase l, that looks like the number 201. Very deceptive for other programmers. Never do that. Use the capital version so they can tell what's going on. To make something specifically an unsigned integer, you can use the suffix capital U. Again, lowercase works just fine too, but for consistency with the capital L, I don't think I've ever seen anyone use the lowercase u. When you declare long data types, this number here is approximately 1 trillion. It's bigger than will fit in an integer. Just wanted to show you guys that this also works. It's not going to give me any errors or any warnings. When I declare short, I don't need to add any special suffix whatsoever. It just give it a decimal number. All right, let me just go ahead. We'll write this. We will compile it. Whoops, G++. I forgot I can't do that. Lecture 04. There we go. Plus %. I think that does work. I forgot the, yep, it totally worked. I just forgot the exclamation point. Then we'll run this. What did I do wrong there? ./a.out. That should totally work. Why did it not run? Oh, it did run. I didn't print anything. Okay, so it ran. It didn't give me any compiling errors. I didn't actually print anything out. Let me go ahead and print some stuff out. That's this section right here. So we'll get rid of the comments. So I just want to talk a little bit about initialization here. There's 4 different ways that we can initialize primitives. The way we've been doing in all of my examples so far, just using the assignment operator equals, I can give a variable a number. I can also use the function style initialization, where I'm just giving x2 a parameter. This also works. Neither one of these will check the size to make sure that the number actually fits. So just as a demonstration of that, I've got x3, and this is a number greater than 2 billion. So it should not fit. And we'll just print that out and see what happens. So let me write this. I made a change. We will compile it. And it does give me warnings here. So integer constant is too large for its type. However, it doesn't stop me. So I can still print this out. So we'll just go ahead and run this. Oops, exclamation. And we see that when I print it out, I'm not getting that gigantic 1.234 times 10 to the 40th or something. Instead, it is converting this. It's using the digit that would have been in the sign bit, and it just happens to be a 1 when I convert this giant number to binary and chop off the most significant digits. So in this case, this happens to be a negative number. So anytime you are assigning a number that's too big to fit in the data, you're just going to get something, it's been truncated, and it'll treat this as an unsigned number, and then convert it to a signed number. So you're going to get basically random garbage if it's too big. Be careful of that. That's up to you as the programmer to make sure you don't screw up. C++ doesn't check it. This is the compiler actually doing the checking and giving you a warning. All right, now, in order to do size checking, let me just uncomment this next little piece here. C++ provides two different options for initialization, and these are newer options. They've been added, well, probably 2 decades ago, but for the first 2 decades of C++, they weren't really available. Maybe even longer ago than that. Maybe, I don't remember. They weren't originally there, but this is known as list initialization. In this case, I'm using the curly braces to put in the value here that I want to go into my data. This curly brace, that list initialization came about when we started using this to initialize vectors or arrays. So that's why it's known as list initialization, even though an integer can only be one value. That's origin of the name. You can also call it curly brace initialization, but this one will check the size. So here I'm just giving it a 0. We can also use the function call style where I skip putting the equals in. This works just fine. I'm going to just go ahead and compile this. I still get those 2 warnings. Let me go ahead and remove this. So this is a warning from x3, but no warnings from x4 and x5. So let me just comment that out. We'll write it. We will compile again. See, no errors this time. And then if I do want to assign a number to x6, this will actually give me, write this, compile, an error. This will crash the compiler, stops me dead in my tracks, and the compiler will not let me do this. It's going to try and take the giant number from the int 128, so that's 8 bytes worth of data, and turn it into an int. Sorry, I misspoke, 16 bytes. Try and turn that into an integer. So I'm just going to go ahead and comment this out. That one will cause the compiler to crash. And then the next topic is losing data when we switch from something that's too big to too small. All right, hold on. Failing at using Vim today. Control V. Down, over, delete. Okay, got it. So what I'm doing here is I'm going to be taking V6. I'll print it out, but that was this number up here. This is much too big to fit into an int or short. I'm declaring a short right here. V7, it's got the value 4. I'm going to overwrite that with the giant number here and just demonstrate that C++ does not stop me from doing this. And in fact, I'm losing data. It's going to keep the least significant bits. So it's going to start over here and keep however many will fit. And because these aren't binary, and we get weird behavior as the sign bit gets overwritten by this. All right, let me just write this. We will compile. Forgot the exclamation. Oh, I forgot to comment that out. Time out. Mangling this today. Sorry about this, guys. Compile. No errors. Good. run it. There we go. So here's the v6 was this giant number, and when it gets converted to a short, there's not enough space in the short to store all of this, so we keep the last couple of digits in binary. We can see that it's truncated it. We're not getting 0, 1, 2, 3. We're getting 1,227 as we lose data. So be really careful about converting different data types when you're downgrading. There's no problem upgrading from a short to anything that's big enough to hold it. There are no problems there. It just copies over and will extend the sign bit so that negative numbers will stay negative, positive numbers will stay positive. There's no trouble with that. All right, I just put together another function to talk about typecasting. For the most part, typecasting in C++ will happen automatically. Don't need to explicitly say that I need to change from one type of data to another type of data, or from one size of integer to another size of integer. It just happens automatically. So here's my example. Focus on these 5 lines right here first. The rest of this stuff is just printing things out, formatting it so it looks really good on the screen. But here's the idea. I'm going to create a Boolean and assign it a number that's not 0 or 1, that's not true or false. I'm going to give it a number. We'll see what happens when we print it out. The next thing I'm going to do here is I'm going to take a floating point number, 3.14, and assign it to an integer. So floating point number assigned to an integer, give you a hint, it's going to turn it into an integer automatically. Then I'm just switch it back. I'm going to take that same integer and assign it to a double. And what we'll see is that it doesn't retain any of the extra information. It's just lost right here when we do that conversion. Then I'm going to talk about unsigned to signed conversions. So if we take a signed number like -1 right here, stored in x1, and we assign that to an unsigned number, this is going to happen automatically. But this is the one that gives us some really weird behavior. So let me go ahead and put the focus back on the Vim instead of the recording software, and we'll just, I already compiled this. All right, so when I run this, I can see here that if I assign a value that's not 0 or 1 to a Boolean value, non-zero numbers are going to be treated as true, and the Boolean will store that as the number 1. 0 is treated as false and will still be stored as 0. Here we go. The integer, when I take a float and cast it to an integer, we lose all of the extra information about the decimal, the 0.14. When we switch it back to a double, that information is lost. We still see that p is now just going to be 3, even though p is a double, and we originally gave the integer d 3.14. That information was lost. Here I'm just creating a variable x1 that's negative so that I have something, a negative number, to turn into an unsigned number. So x2 here actually changes into the largest possible number available to an unsigned, because it takes that sign bit, which is a 1, and converts it into the most significant binary digit. So again, anytime we're looking at negative numbers being converted to unsigned numbers, we see weird behavior. Positive versions work just fine. All right, now I'm going to activate the next part of this code. Take those out, those out. So this is just that signed to unsigned comparison. So here I'm just going to be comparing -1 is less than 1u. The u is going to turn this into an unsigned number. And what we'll see when we do comparison is that the signed numbers are automatically converted to unsigned numbers, no warning from the compiler, and then bool alpha just means that this will print out true or false. And then I'm going to print out the result of this operation. It should be true or false because it's a relational operator. So I'm going to write this. We'll compile it, no problems, and then we'll run it. All right, here we go. So that's added signed to unsigned comparison section. We see that -1 is less than 1 when it's unsigned. That should be true. -1 is less than 1. But when we do this comparison, it converts the -1 to this super large number right here. That number is not less than 1, so we get false. All right, let me activate the next section here. So this, I'm going to focus on integer division here. I've got all of the commands here. They're just going to print out what I'm doing, and then I do the same thing. So let me go ahead and we'll just look at this in the output mode. You guys can come back and stare at the code on your own, or push pause. Let's see here. I need to compile. No problems. And run. Okay, so that's added this integer division section down here at the bottom. So when I do 23 divided by 4, if they're both integer numbers, C++ is going to default to integer division. It's not going to automatically convert to floating point numbers. So 23 divided by 4 is going to be 5, remainder 3. So here we see that we get 5. When we do the modulus, the remainder here is going to be 3. That works great. The problem we run into is that integer division with negative numbers will either round towards 0 or away from 0, and it depends on the hardware. It's paired with what happens with the remainder. So in this case, on the CSL machine, we see that minus 23 divided by 4 actually gives us the negative 5. So it is rounding towards 0. That is the default version that Java uses. But it depends on the hardware. C++ is going to let the hardware take care of this because using hardware is faster than forcing it to be a particular result using software. The only caveat here is that the integer division, that one, is paired with the modulus, so that this must be true. So if I take, in this case, 23 divided by 4, this is going to give me 5. If I multiply that by 4, I should get 20. When I add in the remainder, which was 3, it needs to get the negative 23 back. So I can't round towards 0 and then have the modulus not match up. Those two are paired, and hardware is designed that way also. All right, let me push enter, go back. I've got one more little topic here under typecasting, and so far all my examples have been with integers. We'll see that this works for many other things. We can treat characters as numbers, and frequently programmers will do that if they have like very small numbers or very limited memory. They'll use character and then just use do all the math they need to with a character type because it's only 1 byte. All right, but here, explicit typecasting. The way this works, I'm going to just grab an integer, and I'm going to turn that integer into an unsigned number. We've got 3 ways to do that. I've got all 3 demonstrated right here. This is the original old school version first, where you take the type that you're casting to and put it in parentheses, followed by whatever it is I'm doing, the variable that I want to change. This is the function call style, where I'm treating unsigned as like the name of a function, when in fact it's the name of a primitive, and giving this as an argument to that. This is the preferred way to do things. So most programmers will recognize this and read it more quickly than reading this version. It just makes more sense to people. If you're doing this in the middle of a code, if you want to be able to find all of the conversions very quickly, because this does look like I'm creating a variable, like initializing something, declaring a variable. If I'm typecasting, frequently programmers will use this much longer version, static cast. And also, this version is only allowed to be 1 word, so we must use the shortcut. So if you're casting something to like a long, you will need the static cast so that we can have more than 1 word inside the type specification here. This is a templated function that I need to put the type inside the angle brackets. Name is static cast. It's easy to search for in your code. And the static means that it's going to happen at compile time. So the compiler will take care of all of the type conversions for us, and the code's going to run quickly. There is another version, dynamic casting, and we will talk about that when we discuss polymorphism and inheritance coming up during the last 5 weeks of the semester. That's going to let us choose which kind of data we want while the program is actually running. So the compiler doesn't know yet. At runtime, it'll let us switch and do the casting that way. Much slower, but sometimes you need that. All right, just thought of one more thing before I move away from typecasting, and that's if I want to treat something, so this would be, there we go, get the focus right, integer division. If I want to do this as a floating point division, I just need to convert one of these numbers to a float. And it can be the numerator or the denominator. In this case, my example here, I'm converting the 23 to a float, so it's going to turn into 23.0. And as soon as either operand to the division is a floating point number, it's going to use floating point division. So let me just run this and demonstrate that this totally works. Even if we're using literals, if we use variables, it doesn't matter. So colon, get that out. There we go. So right here, this is the new result. It's going to take 23 divided by 4 and get the answer 5.75. So exactly as we'd expect for floating point division. All right, moving on to the character data type, we'll see that by default, the character data type is 1 byte. This is an absolute 1, not a 1 or greater. Depending on the compiler, this can be either signed or unsigned. And we'll just use single quotes to indicate a char. I'm not going to go demo that. We also have the signed version and unsigned version. And like I said earlier, frequently, if you're working on a machine with very limited memory, like an embedded processor or on an engine or something, you may want to use math that preserves a lot of memory. And so programmers will choose signed characters or unsigned characters to do math with numbers of these very limited sizes. C++ also provides wide characters, typically 2 or 4 bytes. And the idea is that we can either represent Unicode numbers, or if you have 4 bytes, any character in any written language in the world. So basically, the default, the way that the C++ language specification says, the goal is to be able to represent any character in the extended character set of the machine. And to get a wide character, we need to use the prefix capital L here to indicate that. And then the character is, again, just in quotes. I've run into this a number of places in my career as a programmer where we're trying to make the software universal worldwide, available in any language. So this is not that uncommon. During this course, I'm only going to be using ASCII characters, so we'll never see this again. And then C++ also provides char16t and char32t, and these again are absolute, designed to represent Unicode characters, which is the default in Java, so 2 bytes, and 4 bytes for any character used in any natural language. All right, real quick demo of just one thing. Let me switch back over to Vim. What I've done here is I've gone and modified my type properties and just used, we're going to be using char as what we're printing out all of this stuff. So let me go ahead and just write this, compile this, get it compiled, and run it. All right, here we go. When we're looking at minimum value for char and maximum value, the type properties function, the numeric limits, doesn't have char maximum and minimum values stored in it. But we can see from here that it is signed, and that depends on the architecture. So we'll be getting the -128 through +127 as the potential values. And we see that we only get 7 bits for the character. So, and there's no infinity again. So it must be a Linux thing that doesn't provide positive or negative infinity. All right, next up, floating point numbers. I want to do very little here other than mention that the size of floating point numbers, typically 4 bytes, typically 8 bytes. The long double is also available, typically 8, 12, or 16 bytes. This gives us more precision the more bytes we use. They're all signed. There's not an unsigned version. To get a floating point number, we can write 32 with the lowercase f as the suffix to force this to be a floating point, as we do, when we use it as a literal. The double doesn't require any sort of suffix. And to force something to be a long double and use that extra memory, capital L is the suffix. All right, that's all I need here. All right, I want to move on now and start talking about the enum data type. So here I've got an enum demo. I'll put that in main, commented out everything else, so this is all we're getting. Basically, an enum is a little different from Java. In C++, it's going to be just creating an integer data type that has named constants. Okay, so in this case, I've got creating an enum. I'm naming this new data type color, and I'm giving it these very specific values. Okay, these are the only values that anything of data type color is going to be allowed to take on. Okay, and this is exactly the same thing. This is going to be assigned the value 0, the 1, this is a 2. So they're just going to be in order. Red will be 0, orange 1, yellow 2, whatever, as I keep going, 3, 4, 5. And essentially on the inside, this is what it's doing. It's creating a constant int red is equal to 0. Now I'm using capital letters here. That's a convention that's commonly followed by programmers. You can use any variable name you want, but named constants are frequently capitalized. If I run it like this, I will see that this is actually creating a named constant red, and this will be a violation because I'm redeclaring red. Let me just go ahead and do that. Write this, we will compile it. We'll compile it and see that we get a whole bunch of errors. Constant int red, redeclared as a different kind of entity. So I've already got a red right here. So in order to make this work, I need to comment those back out. Okay, so the next thing I'm doing, how do I use this? I'm creating a variable of this brand new data type color. I'm going to name the variable my color. So this is just like creating an int x. Instead, I'm creating a color, my color, and I'm giving it the value red. Okay, I'm only allowed to give it values from this list of things. So, and I can use numbers 0, 1, or 2, or I can just use the name constants. That's the whole point. We're naming the constants, so I don't have to remember what number I assign to the color red, or whatever it is I'm doing. And if I just print this out, I can see that on the inside, my color is actually just stored as the number 0 in this case. So write this, compile it, no problems, run it, and here I can see my color equals red. All right, I mentioned before that we're not allowed to use red anymore as a variable. It's already been declared. Can't use orange either. I cannot use it in another enum either, even if I'm using it as the same number. So if this were 0, this were 1, this were 2, if I had orange equal to 1, I can't do this. It's going to say redeclaration of orange as a different data type. This will fail. So write this, prepare for a giant compiler error. Again, orange conflicts. I've already declared it. Oh, and this, hold on, let me get another example ready. All right, so as I create an enum data type, I am allowed to assign it whatever numerical constant I want. So in this case, I'm creating transportation, and I've got several different kinds of transportation here. So the default value is going to be 0, 1, 2. But here I'm replacing, the plane would normally be 1. I'm going to give it the value 13 instead. And it doesn't have to be in order. Any kind of number will work. I can say boat is equal to 3. And then bike will just increment from there, so it'll be 4. And if I have like another dozen things, I'm totally allowed to reuse the number 13 for another named constant. Again, it's just doing this up here. But when I create the variables, they must take on one of these values. So here in continuing that, I'm just creating T1 is equal to car, T2 is plane. They're just these things. And this is just me demonstrating that I get these numbers as I just said. 0, 13, 3, and this should be a 4. So let me go ahead and run this. There we go. Here's my testing of it. It worked. And I see that I get 0, 13, 3, and this just increments to 4. One other detail using enum data types, I'm actually not allowed to use the numbers. I'm only allowed to use these words as the assignment for transportation. I can compare to integers. When I print them out, they're integers, so it's a little deceptive, but when I'm creating a new data type, transportation T5, if I just try and assign it to car, I can't use the 0. If I try and assign a number that's not an option, both of these will give me errors. Let me go ahead and write this and compile. I think, yep, right here. And I see that I get errors. So the error, invalid conversion from int, which is my 0 here, to this type, transportation, not allowed. I need to use the actual words. So only things from that list are permitted. All right, I just want to introduce the switch expression right here. Normally I would have put this when I talked about the for loop, while loop, if statements, but it really goes very well with enum, so I delayed until I talked about primitives, introduced enum, and this is where I almost always use enum data types. All right, so the basic syntax for a switch statement begins with the keyword switch, followed by an expression. And an expression in C++ is going to be, for this case, anything that evaluates to an integer. We could use a variable, we could use one of these enum variables, like car, for example. So, and then we'll have a number of different cases. The switch expression is going to examine the first case. This constant expression here is just going to be another expression that's something that evaluates to an integer, and it needs to be constant, and all that means is that the compiler needs to know when it compiles what number to use. It can't have variables that accept user input or that it can't figure out when it compiles the code. It needs to replace this with a number. All right, and then for each case, we'll have a number of statements. When I write these, I always put them in brackets. Those are not required. And then followed by an optional break. The break will get out of the switch statement and just continue on after the closing bracket of the switch, paired with that one. If we use break, it jumps down. If we look at this example here, let me take out this break. Just leave that out. if this constant expression happens to be equal to the switch case, the switch expression, then it'll choose this option. It'll do these statements, and then it's going to fall through and continue with these statements also. It's just going to keep running until it hits the break. All right, and then finally, if none of these are true, there's an optional default, which it's going to take this path and I'll execute these statements. There's not a break required because this is the one that needs to come last. All right, I'm going to just fail to type the right thing. Here we go. Comment this out. This is my how to use switch, the syntax. And I've got an example here. So with my, there we go. With my transportation example, all of these things need to evaluate to an integer. So all I'm going to do is put them in a loop. I is going to go from 0 to 14. Some of those will not be valid numbers. So here's my choices. 0, 1, wait, I'm looking at the wrong line there. 0, 13, 3, and 4 are the ones that'll give me things. I've got default here that'll catch all of the rest of them. So I'm just using a for loop. We're going to try a bunch of numbers and print some stuff out. My switch here is going to be based on that I. Now I could stick the word car in here. I could be an enum variable that evaluates to a constant, like transportation T2 is equal to plane. I could use T2 here. In the case of the car, it just prints out you've selected car with a break. In the case of plane, you've selected plane, no break. So it's also going to print out no break after plane, you've selected plane or boat. So I'll be getting 3 lines of text if I choose plane. And quick reminder, plane was 13. So that'll be near the bottom of this list. In fact, it's going to stop before it should be the very bottommost one. If I select boat, it's going to remind me that there's no break after plane, and I've either selected plane or boat. And finally, if I choose some of the other numbers that don't have values here, for example, bike at T4, that is going to be number 4, or any of the numbers that are not listed here, like we have 0, 1 and 2 are not available, 5, 6, 7, up to 12 are not available. So we should get a lot of you have not selected car, plane, or boat. All right, let me just, oh, and I don't think I mentioned that enum is short for enumeration, and that's because I'm assigning numerical values to all these things. That popped in my head while I was eating lunch a moment ago and remembered, oh, I need to say that. All right, we'll write this. We will compile it. And then let me clear screen. And then we'll run it. All right, here we go. So as we go through the list, this is what was printed before. It's just a great reminder of what numbers are things. And when I is equal to 0, it's going to say you have selected car. 2 and 3 are not valid choices. When I get to 3, that's going to be the boat selection. It's going to remind me that there was no break after plane, so I could have selected plane or boat, either one of them. And then 4 through 12 are not valid choices, so it's going to go to the default version. And then finally, when I select 13 for the plane, that's the one that didn't have the break. So it knows absolutely that I selected 13 for the plane, but then it also knows there's no break after the plane, so I could have selected boat because it's going to fall through and do that next case. All right, I think I'm going to wrap up here for today with just one last topic about functions. I want you guys to be able to start writing global functions for your homework. It makes things a lot easier to encapsulate the pieces of code that you want to reuse. So I feel like I need to go over the basics. And then we'll talk more about functions next time as we begin different parameter passing modes. All right, but for the basics, here I have 2 pieces in my function basics. I'm going to comment these out in a second, but these are sort of the basic syntax that's required for a function. So C++ needs to find the function declaration before it is ever used. And it really only needs to know a couple things. It needs to know the return type of the function, so it can decide if it's getting, if it needs to do any casting or to assign it to the whatever variable type we're returning. It needs to know the name of the function, and then it needs to know the types of the parameters. And optionally here, we can name those parameters in the function declaration. Now, when I've been writing all of my code, I have my function declarations up at the top. This is a pretty standard way to organize your code, because then C++ knows all of the function declarations. It knows the return type, the parameter list, and the names. That's all it needs to compile the code. It doesn't need the definitions until later. And then here I'm calling the functions. Oops, I renamed this. function basics. Okay, so this declaration needs to be found before I ever call the function. Then the definition is where I have all the statements. There's absolutely no reason I can't use the function definition up here instead of a declaration. I can substitute the version that has the statements if I wish, and then leave out the declaration. Totally possible. Note that all of these functions are in the global scope, which means they're accessible from anywhere. I'm not required to put functions inside a class like I am in Java. Apologize, my phone's going a little crazy there. I don't know if the microphone picked that up or not. All right, so when I have the definition of the function, this is going to be the one with all the statements that tells the function what to do when it's called. Still need the return type, still need the name of the function, and now the parameter list needs to include the names of all of the variables that we'll be using in the body of the function, or that are going to be passed in as arguments from outside. I misspoke. We don't actually need to use them here, but we need to pass them in. The body of the function is going to be the list of statements, and then we'll either just have a return without a return type, or we will be returning something that has the same type as listed right here as the return type. All right, so as an example, I'm going to go ahead, I'm going to comment this out. Not like that though, do it like this. Control V to give me block mode. Hold on. Control escape to get to command mode. Control V to get to block mode. Scroll down with J, Shift I to get to insert, and 2 slashes. There we go. Okay, so those aren't valid code. That's just me needing somewhere so I can talk about it. All right, so now I've got a function that I'm going to be using as my example. 2 inches. It's going to take someone's height in feet and inches and just turn it into inches. So here's my data I'm going to be using when I pass it in. I'm 6 feet tall and about a ½ inch, so we'll round up to 6 feet 1 inches. That will let me use integers. And then it's just going to convert the, so I'm reusing the variable inches here. It starts out at 1. 6 feet 1 inches, so 6 times 12 is 72, plus 1 more, should be 73. I'm just going to reuse this variable and overwrite it. And then it's going to print out, Mike, should be 73 inches tall, unless I've screwed up. All right, so here's my function. I need to know that I'm going to be using this 2 inches function before I ever get to this line of code. So as it goes through, the compiler needs to find it. And the compiler, it really goes through 4 stages when we do the compilation. First thing it does is it goes up and takes all these include statements and copies them in. Also in that pass, it's going to do all of the preprocessor directives. We'll talk more about those as time goes on when I come up with a good example. But we can use variables and give the compiler commands to control how it's going to compile things. It also is going to remove all of the comments at that time and just leave the code. The next phase is actually, it's going to make one pass through and convert all of this code to assembly. Next pass will turn that into the machine code. But all of this is just a one pass kind of system. So C++ needs to know ahead of time about all the functions that I will be using. It's just like declaring a variable before we use it. All right, so let's take a little deeper look. Here, I've included the optional names of variables. I do this all the time just as a reminder to me. I think it's good practice, but they are not required. In fact, I can delete these, and this will be perfectly valid syntax. This is the minimum that C++ needs to know. I'll go back and put those in before I send this to you guys, if I remember. And then down below this, I have my function definition. This is the one with the curly braces that have all the statements. Now, I picked converting feet and inches to inches because it's pretty simple. There's not a lot going on here. But I wanted to do this to demonstrate a couple of other concepts. The return type for this function is int, so I need a return statement. If I leave this off, C++ will complain. The formula for converting feet to inches is just 12 inches per foot, so times the number of feet plus inches. But I've got my parameter list here needs to have the number of all the parameters I'm going to be using. I'm not changing anything, so this is a good idea to put const right there to indicate that I'm not changing. If these are const variables up at the top in my declaration, I will also need to include the const. And a quick reminder, I don't think I've said it yet. Anywhere you can stick the word const will make your code go faster. Anywhere you can put it in. C++ can choose better options when it compiles if it knows it's not a variable that will change, and it will go faster. All right, let's see here then. So I've got my feet, inches. I also have a default parameter specified here. So if you're familiar with Java, this should not be new. Beginning on the rightmost parameter, I can declare this as a default parameter, and then I can work my way to the right. I can't have a variable without a default parameter after one that does have a default parameter. C++ will complain. But what this is going to let me do, it's a form of polymorphism where I can have more than one way to call the function. I can either call it with feet and inches, or I can call it with just feet. I'll demo that in a second. But let me go ahead and just make sure this compiles and runs. So we'll save it. I made some changes. Just do it that way. We'll compile it, no problems. And then we'll run this. Whoops, missed. All right, so yep, it tells me, Mike, you are 73 inches tall. Perfect, that's exactly what I wanted. All right, so next up, I'm gonna add one more little detail. I'm gonna take out these inches right here and just pass in feet. So now, when this function is called, it should choose to use the default value of 0 and tell me I'm only 72 inches tall. Let me write this, compile it. Oh, I have a typo here. Timeout. What did I do wrong? All right, figured it out, but this is valuable. So remember I told you that C++ needs to know all of the parameters before I get there. So up here I had my 2 inches. It looked just like this. C++ at this point knew that I needed to be giving it 2 parameters. So when I got down here and called it like this with only 1, I got the error message, too few parameters. So up here where I declare it, it needs to know that there is a default value of 0 inches for this. And while I'm right here, I'm going to go ahead and put my variable names back in. I have a strong preference for having these available in my function declarations. They are optional. I don't need them, but I strongly prefer that. Okay, and this only needs to be in one place. So down here in my 2 inches, I took out the equals 0 from the definition. So, Mike, you need to remember that it goes in the declaration, not the definition. I'm probably going to screw that up again, but it'll be educational. So, all right, let me make sure this works now. Write this. We will compile it and clear the screen and run it. All right, so now it's working. It chose to use the default value of 0 inches instead of the inches down here from 1. All right, a quick note on scope. As I declare variables, these variables are only available inside the function body here. To use global variables, I need to declare them up here outside of main, outside of any function, but it's totally allowed. Global variables are, I prefer to minimize my use of global variables. It just gets very confusing very quickly to have a lot of variables that are in scope at any given time. So these variables are not declared as global. These are going to be parameters. So the argument here that's passed in feet is going to be assigned to this variable feet, and they could be different variable names, and I'm allowed to reuse the variable names. So this feet is only in scope in this block. This feet is only in scope inside the function. It's just taking the value here and copying it into feet. Same deal with inches. When I had the inches version, it was copying the 1. It's not calling it with that. Instead, it's going up here, grabbing this 0 as the default value, and copying it into the parameter inches inside the function definition. And then it's just using those values. The moment I hit this return statement, it's going to evaluate this, copy it somewhere special in memory, nuke all of these variables. They are gone. The only thing I saved is this one number, and it's saved somewhere else. And then I return that number so that the function call right here is where I called it, goes and grabs the number that this function stashed somewhere special. So at this point, all of the variables, all the information used to compute it is gone. It's just copied back here into inches, and then I printed it out. All right, at this point, guys, I feel like I've rambled on for at least an hour. Let me go edit the video, put it together, and see how long it is. But I doubt I'll be coming back to record more about arrays. We'll just do that in the next lecture. All right. Gosh, I think this is probably the best I have felt in the last 2 weeks. Today just feels good. And once again, I apologize for how late this stuff is coming out. My plan is to get the rest of homework 2 finished up this afternoon, followed by lecture 5 tomorrow morning. At that point, we'll be all caught up. Things will be back to normal. All right. Have a great day.